Today we will solve section B of 1999, and so without wasting time we will see the question. So very first question we have, it is proposed to produce acetaldehyde by the oxidation of ethanol in the gas phase. So we have these reactions. Okay, the ratio of air to ethanol in the fresh feed before it is mixed with the recycle, that is obvious, is 10 is to 1. Okay, the conversion of the ethanol on single pass through the reactor is 25. So I have told you in the earlier when we were solving 1991 2 3 and 4 and in the previous years, that what is per pass and what is overall conversion. Okay, so before going through these type of questions, recycle member, you need to know about the per pass one, per pass and overall conversion. Okay, the unreacted ethanol is completely separated from the reaction. So here we are only separating unreacted ethanol. The air and the nitrogen we are not recycling. Okay, only unreacted ethanol is recycled here. Okay, so what is the ratio of recycled stream to fresh stream? Okay, so but in fresh stream we have both air and ethanol, but in the recycle we only have ethanol. What is the composition of outlet stream from the reactor outlet stream in mass fraction mole fraction? Okay, we'll see that. So very first, this is our flow diagram. So this is F, you all know, this is M, and this is recycle. Recycle we only have C2H5OH. Here we have CH3CHO. Okay, converted. Okay, so here 10 is to 1, air and C2H5O. Okay, so let's see. Rate of ethanol in F 1. So for maintaining the ratio, air should be 10. Okay, so balance at 0.1. This is the balance at 0.1. M is equal to F plus R. So but total F is equal to 10 plus 1, that is 11. So and let R be the recycle, right? So M is equal to 11 plus R. Straightforward, nothing rocket science, straightforward. Since R be the recycle, so only ethanol in the mixed feed will be R plus 1. We are saying ethanol in the mixed feed. R is coming from the recycle and 1 is coming from the fresh feed. Okay, R is coming from the recycle and 1 is coming from the fresh feed. So it equal to R plus 1. Ethanol reacted 0.25 R plus 1, straightforward. Unreacted 0.75 R plus 1, that is R plus 1 minus 0.25 R plus 1. So 0.75 R plus 1. This unreacted should be equal to R because we only have ethanol in the R. So R is equal to this. So we have R equal to 3 and the ratio of recycled stream to fresh stream is this. Now this is one method. Okay, we'll see the other one. Okay, and I think this is a little simpler. Okay, so let C2H5OH in M is equal to 100 kmol per hour. What I have assumed that in M itself, C2H5OH ethanol is 100 kilomole. So how much ethanol is reacted? According to the reaction per pass conversion 25, so 25 kilomole per hour reacted, right? Unreacted 75 kilomole per hour. That is ethanol in the recycle, right? Unreacted, that is ethanol in the recycle. So if I will make balance on 1, F is equal to of ethanol balance. We are making ethanol balance. So C2H5OH in F कैसे? How? M 100 ethanol balance. C2H5OH balance. Okay, so 100 is equal to F is we have to calculate R is 75. So F is equal to 25. Okay, so F is equal to 25. If F C2H5OH in F 25, that means to maintain the ratio of 10 is to 1, air should be 250. So air is 250. So total F 250 plus 25, total F yani means air plus ethanol. So 275. So we have ratio of R upon F, that is 75 upon 275, 2727, that is 2727, the same answer. Okay, so this is the same answer, right? So this is, I think this is little bit simpler. Okay, now we have to see the composition, mass fraction, mole fraction. Okay, so very first air in F 250, that is equal to air in M, because no air is coming from the recycle. So same air will go into the M, into the reactor. So O2 in air 52.5, N2 in air 0.79 into 250, that is 197.5, or 250 minus 52.5. Same answer will come. So O2 reacted as according to the stoichiometric coefficient of O2, stoichiometric coefficient of ethanol into 25. Ethanol is reacting 25. So this is O2 unreacted, fed minus reacted, unreacted. So these are the components. So C2H5OH, O2, N2, CH3CHO, H2O. So see, C2H5OH, it is saying outlet of the reactor. So C2H5OH will be, it is the feed. So outlet will be 75 because it is reacting 25. It is reacting 25. So 75 will be outlet of the reactor. O2 will be unreacted at the outlet of the reactor 40. N2 will be the tie component. It is a tie component. It does not take part in the chemical reaction. So it will be whatever in the input we have, it will be the same quantity we have. We will get it at output. 97.5. It is in kilomole per hour. Okay, so and CH3CHO, ethanol reacted 25, so it is the same according to the stoichiometric coefficient 1 by 1 into 25, that is H2O. Now in kg per hour, just multiply it with the molecular weight, you will get this. See, it is kilomole per hour, this unit. Okay, when you will multiply with molecular weight will be x into kilomole per kg. That kg I will take up. So kilomole and kilomole cancel, it will come with kg per hour. Okay, always remember unit and always write in the unit. So this all things. So we have total this and total this, and I don't think so there is much more to explain in this, how to calculate mass fraction and mole fraction, right? So this divided by whole quantity will give the mass fraction. This could divided by this mole fraction for component C2H5OH. Remaining you can calculate. Okay, so this is straightforward question. So switching over to the next question. CaCO3 slurry has to be dried. The dryer is designed to remove 100 kg moisture per hour. Okay, 100 kg of moisture per hour dryer is removing. Okay, air at 20 degrees Celsius. Air at 20 degrees Celsius at 40% relative humidity enters the dryer. When it is entering, it is at 20 degrees Celsius, 40% relative humidity. Okay, and dryer is at 65 degrees Celsius. That's why it is leaving at 65 degrees Celsius and relative humidity 65%. See, the air is going at 20 degrees Celsius with the relative humidity of 40 degrees Celsius. That means it has to be go outside carrying more moisture content, because after drying the slurry, the moisture content will be more as in the leaving air, because it is getting the moisture. Air will get the moisture. Okay, so the relative humidity will increase. Relative humidity is humidity, you know, the moist quantity of water vapors in the air. So it will increase after leaving the dryer. Okay, at 65 degrees Celsius. Okay, see, 65 degrees Celsius is the temperature of the dryer. Okay, temperature of the dryer. So air will get heated up, plus it will also get the moisture. Okay, what is the weight in kg of the bone dry air required per hour? Dry air, kg of dry air. Okay, weight of dry air. Atmospheric pressure is 103 kilopascal. That is the total pressure. If the humidity of air entering dryer can be varied, what is the minimum amount of dry air required? Okay, that is the same thing it is asking. Weight of dry air. The constants of Antoine equation for vapor pressure of water in, this is not 3, this is in mmHg. In mmHg may be taken as A, B and C. Okay, so very first, so Antoine equation, we know that this is the Antoine equation. We'll put the value. Now the temperature is different. at 20 degrees Celsius, at 65 degrees Celsius. So P set at 20 degrees Celsius, when you will calculate with the end-to-end equation after putting all the values and then put T equal to 20, so you will get 2.319 mmHg. P at 65 degrees Celsius, 25.076 mmHg. Okay. Now, percentage humidity, we have this formula. Okay. Pa is equal to partial pressure equal to relative humidity at 20 degrees Celsius is 40%. That means 0.4 into 2.319. We just have calculated P set. So partial pressure is 0.928 mmHg. Similarly, Pa at 65 degrees Celsius 0.65, because 65% relative humidity at 65 degree temperature. So 25.076 we just have calculated this. Okay. So 16.3 mmHg. Now absolute humidity, formula for absolute humidity is, if you will not add this Ma upon n, then it will give molar humidity. After adding this, it will give absolute humidity. Absolute humidity is in kg, molar humidity in moles. Okay, so after putting all the values, absolute humidity at 20 degrees Celsius, we just have calculated Pa. Pt is 103. Ma and Mb we know that. 18 upon 29. 18 is the molecular weight of water, 29 is for air. So we'll get 0.0056 kg moisture per kg dry air. Okay, you understand, hope you understand this, how kg dry air will come. Okay, because this is the moisture. When you will not add Ma upon Nv, it will give the unit of kilomole dry kilomole moisture per kilomole dry air. Okay, after adding Ma upon Mv, it will give kg per moisture, kg per dry air. How it is giving dry air, not wet air? Because with the total pressure, when you are subtracting partial pressure, it will give the dry air. If you will add this, it will give wet air, kg of wet air. Okay. This is basic concept of humidification. We are here to solve the questions, okay, not to see the basic concepts. So okay, fine. So absolute humidity at 65 degrees Celsius is equal to 0.1167 kg moisture per kg dry air. Same. We have calculated everything at 20 degrees Celsius and 65 degrees Celsius in the same manner. Now let dry air required be X. Now X kg is dry air required. So X kg is dry air required. This is the absolute humidity at 20 degrees Celsius. That means when the air will go out, the humidity will increase, because humidity is what? Quantity of vapors in the air. Since we are drying a CO3 slurry, so it will remove the moisture because it is getting heated up. That okay. So air will get the moisture and will go out of the dryer. So 0.1167 will be the kg moisture. Now the difference of this moisture will be equal to the amount of moisture. The difference of this moisture will be equal to the amount of moisture. So X into 0.1167 minus 0.0115 kg. So kg moisture and kg moisture will cancel out and dry air will come here. So this is the answer. Straightforward. Very simple question. So we will see the next question. For a binary system, methanol 1 and benzene 2, recommended value Wilson. Okay, this is Wilson parameter. So it is out of course. Okay, there is a Wilson formula. Okay, like this, I think something Wilson formula. So this is out of course. Okay, I think this is from Rolle's law, modified Rolle's law. No, so we will not do this question. Oil of viscosity 100 centipoise is to be pumped as shown in the following figure. The pipe used everywhere is of 7 centimeter internal diameter. That means velocity is same everywhere. When diameter is same everywhere, velocity is same everywhere. Pump efficiency of pump is 80%. Find the energy required for pumping the oil at this rate, 20 meter cube per hour. Density of oil is 800 kg per meter cube. Okay, power required. Okay, so very first we will see the diagram. This is the diagram, right? Diameter is same everywhere, so velocity will be same. So power required for the pump is equal to, we have rho g q hp. Okay, this formula changes when we have P is equal to rho g QHF. When we have head loss, on the basis of head loss we have to calculate power, then this formula come. Okay, on power we have calculate for pump, then HP will come. So Bernoulli equation is given by this. We know that this is the famous Bernoulli equation. So see, P1 and P2 will cancel out. Why? Because both are at atmospheric pressure. Atmospheric pressure is applying to both. Okay, V1 and V2 will cancel out because velocity is same everywhere, because diameter is not changing. So HP is equal to Z2 minus Z1, 2 meter. So HP is equal to 2.5 meter. Now P is equal to rho G QHF or HP in case of pump. So see, kg meter per second square. What is this? This is Newton. Meter cube and meter cube will cancel. Second into meter. So Newton meter is joule. Joule per second is watt. So it will give 109 watt. Okay. So next question. 150 kg of water is to be heated in a steam jacketed vessel from 25 degrees Celsius to 80 degrees Celsius. Steam is condensing at 120 degrees Celsius. Heat transfer area is 0.25 meters square. Heat transfer coefficient for condensation of steam and heating of water by convection. Okay, so we have heat transfer coefficient for both, for inside or outside. 1000 for steam as well and for water as well in the pipe. 1500. Okay, write appropriate unsteady state balance equation. Find the time required for heating water. Okay, so after applying the energy balance, we know that what equation will come. We will not do the energy balance. Okay, that is you just go through R.K. Rajput, B.K. Datta or J.P. Holman. You will know there. Okay, so this formula will come. T minus Ts, Ti minus Ts equal to E minus UA. See, why U? Sometimes HA upon MCP, HA upon rho VCP, both are same. Rho V is equal to mass. We have to took the mass because mass is directly mass is given. No density and volume is given. Directly mass is given. So MCP. And why U we have taken? Because 1 upon U is equal to 1 upon H I plus 1 upon H naught. Okay, so we have taken overall. So taking log both side. Now U is this we have given. Okay, and you know that this is, what is this? HA upon MCP is equal to 1 upon tau. So tau is equal to MCP upon HA, which we have studied in the instrumentation and process control. So it is R into resistance into capacitance. What is resistance? 1 upon HA is resistance, we know that, and capacitance MCP. Okay, we have studied that, right? Okay, after putting all the values, what is T? T is 80. Why 80? Because it is going at 80 degrees Celsius. TS is 120. T initial is 25. TS is 120. TS, sometimes we take TA, that is atmospheric pressure, atmospheric temperature, in temperature of the atmosphere in which we are with which we are dealing with. Okay, so TS is the atmospheric temperature, that means the atmosphere we have of steam. So after putting all the values, we will get T is equal to this. Okay, so straightforward question, just formula based. If you have basic concepts and good command on heat transfer, there is no problem in solving these type of questions. Okay, so stripping of ammonia is carried out at a pressure of 1.1 atm. 1 meter cube of water enters the system, and the ratio of molar flow rate of air and that of water is 4. Okay, the inlet air and the inlet water have 0.1 and 1.0 mole percent of ammonia. Okay, Murphy vapor plate efficiency for ammonia removal is 50%. Murphy vapor plate efficiency is 50%. The Henry's law constant for ammonia in water is this meter cube per mole, atm meter cube per mole. Determine the exit water composition and exit air composition. That means the composition in exit water and composition in air, exit air of the ammonia. Okay, so very first, GS upon LS we have 4. It is written that ratio of molar flow rate of air to liquid, it is 4. Murphy vapor plate efficiency 50% and H is ATM meter cube per mole. Henry's laws we have. So this is basic Henry law, we know that. Okay, in case of mole fraction, Pa is equal to HA, XA, HA. Okay, in case of mole fraction. So we have concentration. Now, further, partial pressure is equal to Ya equal to Pt. We have seen many times in solving modified Rolster equation. H is equal to Ca is what? Total concentration into composition of a solute. So it is straightforward. There is no need to make you guys understand what is this. It is straightforward. So Y is equal to H upon Pt Ct Xa. So Y equal to M. So what is M here? So M is equal to H upon Pt into Ct. H upon Pt, Ct is rho by M. From where it will come? Refer to mass transfer. Mass transfer, diffusion in liquids. Diffusion in liquids. Diffusion in liquids. Okay, you will know that. Then putting all the values. Now see. ATM will cancel out. Mole will cancel out. Kg will cancel out. Meter cube will. What remaining? This kg is remaining. This is k is remaining, and k is number. So we multiply it with 1000 here. Okay, so 1.3 will come. Now we have Murphy plate efficiency. Okay, so putting this value, we will get x1 from here. Okay, x1 from here. So we will get x1 from here. So what is the value of x1? It is 0.0054. Now solute balance over ammonia. GS is equal to Y2 minus 1. See, this is the case of stripping, and stripping is just opposite of absorption. Okay, so this equation changes a little bit. In the absorption, Y1 minus Y2, X1 minus X2. In the stripping, it is little bit changing. I have uploaded all my notes in the previous lectures. Okay, so go there. When you will go through these lectures, you will know, you will see all those formulas. Stripping and ammonia, it is written in the single page to avoid the confusion. Okay, so after putting all the values, just rearranging it, we'll put in all the values. You will get Y2 is equal to this and Y2 is equal to this. Okay, Y1 is equal to X1 is equal to this. Y2 is equal to, okay, so everything we have. Okay, this is the thing. Now determine the efficiency, determination of efficiency is critical in plate column design. The gas and the liquid rates are 0.1 and 0.25 kilomole per second respectively. Interfacial area of the mass transfer 35 meters square per meter cube. Okay, the residence time of both the liquid and the gas in the froth zone is 3 seconds. Liquid phase and gas phase mass transfer coefficient are 1 into 10 power minus 2 meter per second, 2 into 10 power minus 3 meter per second. Calculate liquid phase transfer unit, gas phase transfer unit, stripping factor, overall transfer unit, Murphy point efficiency. Okay, so liquid phase transfer unit is given by NTUL is equal to KLA/TL. How? Meter cube will cancel out, second will cancel out. So this is the formula. Okay, 1.05. Remember this formula. Okay, for derivation refer Trebol, Robert E. Trebol, Robert E. Robert E. Trebol. Okay, similarly NTUG, this is the formula. Okay, now we have this formula, putting all the values where S is equal to stripping factor. So putting all the values, we will get NTUOG, that is number of transfer overall gas phase. Okay, Now, Murphy point efficiency is equal to actual separation at the point divided by the maximum separation at the point. Yn local minus Yn plus 1 local. This formula, and this formula all are same, and we will see a question on this formula in GATE 2017. Okay, there is a good question of 1 mark, I guess in 2017, I think. So putting all the values, we will get this. So straightforward questions. Okay, two parallel first order reaction, A that gives B, A that gives C, is taking place in the liquid phase, that is E equal to 0, density is not changing, in a well mixed batch reactor. After 60 minutes of operation, 80% of A has reacted, while 2 mole of B per mole of C is detected in the reactor. So moles of B per moles of C is equal to 2 at a certain time. Calculate rate constant K1 and K2 for two reactions. Assume that no B and C were initially present in the reactor. Okay, so very first, this is the reaction. Okay, mark it 1 and 2. Reaction taking place in liquid phase, so E is equal to 0. That is straightforward. Rate of reaction 1, KCA, K1CA, K2CA, right? All reaction K1 plus K2CA. See, don't add these equations. If you will add, the answer will be wrong. It is a logical thing that for first reaction, it is going K1CA and it is decreasing, minus K1CA. Similarly, in the second case, the same RA is decreasing with K2CA. There is only change with the constants, rate constant. So if I want to write overall decomposition, overall degradation of A, so it is going in step 1, step 2. So if I will add both the step, I'll get overall decomposition of A, degradation of A. Okay, don't add these equations, so we'll get this. Performance equation of batch reactor and PFR is almost same, since in PFR tau will come, here T will come, and why T and tau will come, just refer to level spill or Ka Gawane, H. Scott Fogler. Okay, so put all the values, you will get, and after putting the values, you will get K1 plus K2 is equal to 0.268. Now, moles of B per moles of C is equal to 2. If I divide by volume of the reactor, moles of B divided by the volume of the reactor, moles of C divided by the volume of the reactor, what I will get? C concentration of B, because mole per meter cube is concentration. Similarly, Cc by moles of C divided by B, we will get concentration of C. Now in this step I have divided moles by volume of the reactor. In this step I will, after getting concentration, I divided numerator and denominator with T. So what we are getting? dCB by dt, dCC by dt. So ultimately it is a rate. So this will give final. Okay, these all steps, this I just wrote to understand you guys, because it is straight. When it is saying moles of B per moles of C, it is straight this. Just go and write this. The same concept question, GATE 2020 IIT Delhi had asked. Okay, so we have two equations and two unknowns, so we will see. These are the answers. Okay, an isothermal plug flow reactor is designed to give 80% conversion of A for second order liquid phase reaction, A that gives B. Okay, pure A at concentration 1 kmol per meter cube is fed to the reactor at a flow rate of 5 meter cube per hour. Okay, the rate constant for the reaction at a specified operating temperature 0.5 meter cube per kilometer, 5 meter cube kilometer. Isothermal na? Yes, it is isothermal. Okay, because it is saying specified temperature. Okay, so it is isothermal. When the reactor is actually operated based on design, it was found that 30% of initial reactor behave as mixed, well mixed reactor. Remaining is plug flow. Calculate the conversion obtained in such reactor. Okay, so very first we assume after operating we got to know that the reactor is operating 30% initial reactor, 30% mixed flow, and later 70% plug flow. But before reacting we were assuming that it is plug flow reactor, so we will solve it with the plug flow reactor, because initially we don't know that the behavior of the react this kind of behavior will show after when we will run the reaction. So before running the reaction we will solve with the plug flow. So volume equal to 40, right? Volume equal to 40. Now after running, total volume is 50. After running, 30% behave as CSTR. So CSTR is this. Put all the values. Quadratic equation will come here. Okay. And conversion will be in CSTR 0.41. Now the remaining 70% is plug flow. To apply plug flow equation. See, this x1 is equal to 0.41. This. And we have to calculate x2. Okay. So after putting all the values and calculation, you will get 0.78. Okay. This is a good question. Okay. For an exothermal, this question we will not do, because GATE will not ask this type of question. One, it is very lengthy, and second, energy balance in this is important, but we will see those question in after 2000s. Many questions are there. Okay, many questions are there, so we will not see this question. Now a new equipment made of material A cost post installation rupees 3 lakhs and is expected to have a scrap value of 10% of this after the end of the 10 lakhs. Scrap value is something that is going in scrap. कबाड़े में जो दे दिया, राइट? जो रद्दी लेने आता है ना हमारे हम लोग के पास, उसको बोलते हैं स्क्रैप. So after 10 years it has a scrap value of 10% of the initial cost. That is fine. Similar equipment made of material B cost rupees 1.5 lakhs, but it is like no scrap value. Okay. Assume that both type of the equipments could be replaced at a cost that is 20% more than original value. Okay, see, both type of equipment could be replaced. That means at the cost of 20% of original value. That means 20% of original value we have to give to replace the equipment. So there is no need to replace the equipment. This line is only to make you guys fall in a trap. Okay, so this line is a trap. Okay, so this will not come anywhere, because there is no need to replace, because we are capitalizing a equipment. On the basis of equal capitalized cost for both type of equipment, estimate what should be the useful life for equipment made of material B. The company has to pay an annual interest rate of 15%. Okay, so very first capitalized cost is CC. Material A post installation cost rupees 3 lakh, scrap value 0.3 lakhs, N is equal to 10 years number of service life. Material B post installation rupees 1.5 lakh. Okay, this is capitalized cost. Okay, this is capitalized cost. Formula for capitalized, complete formula for capitalized cost. Now this will become zero, this part, because no annual operating cost is there. A is for annual cost. Any annual cost, whether it is operation, either maintenance, or it is some allowances, any annual cost will be add. Okay, so no annual cost, so it will zero. So we have left with only this for material A, material B. So we'll put all the values and we'll solve. we will get NB is equal to 3.5 years. Okay. Okay, so that's all, guys. Section B is having all those questions, and which I have left in the section B are those questions which are derivative type, which we have to derive, and those kind of question gate is not asking anymore. And these question we have done today all are important, and just believe me, we are not leaving any single important question. Okay, but if you want a solution of any particular question, just comment it below the year, the question. I will provide the solution if possible. Okay, so bye guys, take care.